Yeah, welcome back to our next example. So, here we do have the differential amplifier and the load, of course, it is active load, but internally we do have current mirror. So, what we are expecting here it is transistor 7 DC wise it will be mirroring its own DC current into transistor 8, and that is good. In fact, we want this current should also be same as this one from balanced point of view. So, we do not have to put any external circuit to bias it, and in addition to that this transistor 7 it may also mirror signal current in case if we have say GM into VBE current it is coming here at the collector. So, that current is also getting mirrored there. So, it is expected that the signal it is whatever the differential signal or common mode signal it will be arriving to this output through this transistor 2 as well as through transistor 1 and then through the current mirror. So, we will see the consequence in this numerical example. I hope you recall the analysis we have done for this circuit. So, in the numerical examples we will be re-establishing the same thing. To start with we do have to find the DC currents through all the transistors. Again the value of this resistor it is 11.4 K. So, that makes this current equals to 1 milliampere. So, the current flow here it is also 1 milliampere, and if we are applying meaningful input common mode DC, then half of the current it is flowing here and remaining half it is here. So, each one of them it is 0.5 milliampere. So, this 0.5 milliampere it is getting mirrored here. So, the current flow here it is 0.5 through transistor 7 as well as transistor 8. Now, yeah, so it is now it is pretty straightforward. So, if you ignore this early voltage to calculate the nominal quiescent current, namely 1 plus VCE by VA, if you consider it is approximately equal to 1 for DC condition, DC current, then the circuit analysis it becomes really simple. And also we like to say that since this is transistor 7 it is diode connected. So, the voltage here it is decided by the 12 volt minus 0.6. So, the voltage here it is 11.4. In fact, it can be shown that the DC voltage at this point, assuming Q1, Q2 identical, Q7, Q8 identical, it is also 11.4 volt. So, I should say DC voltage at output 1 and output 2 both are 11.4 volt. Now, with this information let me calculate the small signal gain, namely differential mode gain and common mode gain in the next slide. So, yeah. So, our next calculation it is we need to find differential mode gain and common mode gain, and here we do have most of the small signal model. This part of course, we are in the small signal model we are removing, we are keeping only RO 3, and on the other hand for transistor 8 we do have RO 8 and then RO 7. In fact, since it is diode connected we should also keep this RO 7 in parallel with 1 by GM 7. So, the voltage coming here VO 2 it is predominantly it will be defined by 1 by GM7 and whatever the signal current is flowing through this. So, approximately we can say that this resistor it is 1 by GM7. So, then whatever the voltage it is producing here, that voltage it is also deciding the VB voltage of transistor 8. So, through the transistor 8 there will be a current flow, signal current flow, and this signal current flow of course it will be corresponding GM8 multiplied by the VB here, which is it is basically this is VO2, because this node it is ground. So, the voltage VBE voltage it is GM8 multiplied by VO2. So, in the summary, to analyze this circuit we can just simplify and saying that this resistance it is 1 by GM7, this is RO8, but in addition to that we do have a current flow here which is GM8 multiplied by VO2, and then we do have RO1, RO2, then we do have GM1 into VBE1. So, this is VBE1 across this R pi. So, VBE1 here. So, likewise here we do have VBE2. So, VBE2 multiplied by GM2 it is giving the current here. And to get the differential mode gain, what we can see, we can make this voltage equals to V in D by 2, and this voltage on the other hand it is minus V in D by 2. And in fact, this is common node, the impedance looking into this device and this device, if I ignore this part, strictly speaking they are not same. The impedance looking into the source of transistor 1, it is smaller primarily because at its collector we do have a smaller resistance compared to whatever the resistance we do have. In fact, there may be a detailed calculation by which you can find that this voltage it is tilted towards VDD V in D by 2 compared to minus V in D by 2. If the two resistances they are equal, then only you can say this is AC ground, but whatever it is we may say that it is having Vs voltage, that makes this VB voltage which is this V in D by 2 minus Vs. On the other hand, the voltage here it is minus V in D by 2 and then minus this Vs, and then that produces this current, and this current it is producing a voltage. Compared to this impedance, we may ignore this RO1 even though it is connected to this node which is having a signal, but as the signal here it is very small, we may say that output voltage VO2 it is well approximated by GM1 multiplied by 1 by GM7. So, that is the impedance at this node, and then V in D by 2 minus, I should not say is, let it be VE, because this is common emitter voltage. So, that is the voltage you do have here. So, the current flow at this node on the other hand, it will be GM8 multiplied by this voltage which is GM1 by GM7 with a minus sign multiplied by V in D by 2 minus V E. So, this is the current at this point. In addition to that, we do have this current also. So, we do have GM 2, and then we do have minus V in D by 2 minus V E. So, this is the total current, and if I multiply this current by the impedance at this node, which is practically it is R O 8 in parallel with R O 2. So, that gives us the output voltage V O 1. In fact, if you see here GM 7 and GM 8, we may cancel it out, and if I consider GM 1 and GM 2, they are equal, then this we do have a minus sign here and minus sign here, that makes it is plus, and here we do have minus sign. So, we can say even this part is also getting removed. So, with this approximation, what we are getting here, it is GM 1. So, we do have GM 1 here, and then of course, with a minus sign here, because the current is departing this node. So, we will be having a minus sign. So, this minus sign and this minus sign and this minus sign, they are getting converted into plus. So, eventually GM 1 or GM 2 multiplied by this V in D multiplied by this net output resistance, which is practically R O 8 and R O 2 in parallel. So, if I say that final output voltage, if I call this is the net output voltage V O 1 by differential input here, which is equal to G M 1 or 2 multiplied by R O 8 in parallel with R O 2. On the other hand, the voltage at this node V O 2. So, V O 2 on the other hand, so this is equal to it is very small. So, whatever the voltage you do have, that is getting multiplied by G M 1, but then that is again multiplied by 1 by G M 7. So, this is V in D by 2 minus V E, but whatever it is, these two GMs in the same order of magnitude. As a result, you may say that this voltage it is very small compared to V O 1, and if I say that output voltage differential output voltage V O D defined as V O 1 minus V O 2. So, all practical purposes it is equal to V O 1, and then the expression of V O 1 it is given here to find the gain, differential mode gain A D. So, that is equal to, that is defined as V O D divided by V in D, and that is given by G M 1 into R O 8 into in parallel with R O 2. So, numerical value, to calculate numerical value, let we consider let we calculate G M 1 and G M R O 8 and R O 2. In fact, we already have done this calculation. G M 1 equals to 0.5 divided by 26, and so this is this much of mho, and R O 2 equals to 200 K. Also R O 8 equals to 200 K, and that gives us the differential mode gain equals to 0.5 into 100 divided by 26. So, that is equal to so this into 1000. So, this is equal to 50 I should say 50 divided by 26 multiplied by 1000. So, that is 1923 to be more precise. So, that is the differential mode gain. On the other hand, the common mode gain. So, the common mode gain, it is essentially it is a bit tricky. Here we do have this resistor, it is practically 1 by GM7, and if we apply same voltage here and same voltage here, namely V in C. So, that makes this voltage and this voltage to be equal. So, even though we do have RO 8 connected here, but we do have voltage dependent current source which depends on this voltage, making this node very insensitive, or a smarter way to calculate the common mode voltage. You can see that common mode gain essentially it is VO2 divided by V in C. And in this circuit, since we are applying same voltage here and here, V in C with same polarity, in that case this node, of course, it is remaining high impedance or rather I should say degenerated node. So, we do have this resistor remaining there, and it is degenerating the circuit, and this gain, as we have discussed before, it will be the gain of this circuit which is getting degenerated by RO3, or if I split the circuit, it will be rather 2 times of RO3. So, the corresponding gain here it is GM1 multiplied by 1 by GM7. So, that is the impedance here, divided by 1 plus GM1 into 2 times RO3. In fact, this GM1 after removing this 1, you can remove this GM1 also. So, that gives us a common mode gain equals to 1 by 2 GM7 into RO3. In fact, GM7 it is given to us and also so it is becoming this is 26 divided by 2.5 milliampere, 2 into 0.5, and then RO3 it is 100 K. So, that gives us how much? 6 into 10 to the power 5 minus 5, sorry. So, the common mode gain it is really very small. So, that makes this circuit it is having differential mode gain it is good, and then common mode gain it is quite low. The similar kind of circuit can also be constructed using MOSFET. So, in the next slide we will be talking about that. So, here again we are assuming that these two transistors they are identical, these two transistors they are identical here, and the load part also it is active current mirror load, and they are also identical, and the supply voltage it is 12 volt, bias resistor it is 9.5 K, and let me consider all the lambdas are 0.01 per volt. threshold voltage of all the transistors, it is equal to 1.5. The analysis part, it will be very similar to the other circuit which just now we have discussed, having BJT implementation, but probably the DC operating point may be little different. So, let me calculate the DC operating point. We do have 12 volt supply here, and we do have the size of transistor 4, it is given here, rather transconductance factor, it is 4 milliampere per volt square. If we calculate it carefully, what you can get here, it is the current flow, it is actually it is equal to 1 milliampere. So, 4 is it 1 milliampere? This is 3 and 4, they are equal, that is fine. Let me calculate this one. So, we do have the VDD minus Vs or VGS of transistor 4, and so that is equal to this R bias multiplied by this I, and so this I reference. So, this I reference on the other hand, it can be defined by this transistor. So, we do have R bias multiplied by 4 milliampere by 2 into VGS minus VTH square, and so here what you can do, we can subtract, so we can add 1 VTH and then subtract 1 VTH. So, we can say VDD minus VTH minus VGS 4 minus VTH equals to we do have 9 here, 9.5 here, and then 2 here. So, that gives us 19 into VGS 4 minus VTH square, and this part it is 9.5. So, we can say this is 9.5 minus, let you consider this is x is equal to 19 x square, right. So, from that we can find what will be the corresponding x. So, we do have 19 x square plus x and then minus 9.5 equals to 0. So, from that we can find what is the x, and then you can consider these two are having current mirror. So, obviously, then you can find what will be the current flow here, and then half of the current it is flowing here. So, then here also the corresponding current it will be half of that. So, that is how we can proceed. Probably you can work it out, and once you get the operating point, then you can find the differential mode gain, which is again GM into RO2 in parallel with RO8, and the common mode gain on the other hand, it is AC equals to minus 1 by GM7 into 2 into RO3. Probably you can work it out. So, since it is similar kind of example, so I will skip that part. So, yeah, so this is, and then you can probably you can find what will be the numerical value. Now, coming to the conclusion of this entire session, it is what we have talked about. Basically, we started with numerical examples of simple current mirror, and we have calculated the different transistor current there, and then we have talked about numerical examples of improvised current mirror, namely the beta helper and then cascade current mirror. And then we have talked about different numerical examples on amplifier, starting with common emitter and common source amplifier having current mirror as its load. And then we have talked about differential amplifier implemented by BJT as well as the MOSFET. And then there we have considered how to calculate the quiescent current of all the transistors, and then we have calculated the differential mode gain and common mode gain. I think that is all to share with you. Thank you for listening.